Calculating the service size from the utility company for a mixed-use building requires understanding the load calculations for both the non-dwelling, which are the retail spaces, and the dwelling units, which are the residential spaces. The minimum service size is determined by summing the individual loads of these spaces. We'll walk through the process step by step. Firstly, let's consider the non-dwelling service load for the retail spaces. The calculation determines a minimum service load of 175 volt amps for retail space A. Given that the other two retail spaces are approximately the same size, we can assume a similar minimum service load for each of them. To find the total non-dwelling load, multiply the individual load by the number of retail spaces. In this case, 175 volt amps times 3 equals 525 volt amps. Secondly, we calculate the dwelling unit load for the residential spaces. The calculation determines a minimum service load of 110 volt amps for residential space RA. Assuming the other residential spaces are approximately the same size, we can calculate the total dwelling unit load by multiplying the individual load by the number of residential spaces. That is 110 volt amps times 3, which equals 330 volt amps. Thirdly, to determine the total building service load, sum the non-dwelling and dwelling unit loads calculated previously. Adding 525 volt amps, the total retail load, and 330 volt amps, the total residential load, gives a total of 855 volt amps. Now let's consider sizing the service entrance equipment. While the calculated service load is 855 volt amps, selecting service entrance equipment with a rating less than 100 amps is generally not practical. Therefore, selecting a meter pack center with a 125 amp circuit breaker is a more appropriate choice for the service entrance equipment. It is important to consider what happens if one of the units demands more load than anticipated. If a retail or residential unit requires significantly more than the calculated load, for example, more than 200 amps, it is important to investigate the specific load requirements of that unit. This might involve analyzing the equipment being used, the operating hours, and any potential future load increases. Depending on the findings, it may be necessary to upgrade the service entrance equipment to a higher amperage or even provide a dedicated service for the high demand unit. Consider factors contributing to higher load demands. Firstly, the equipment used within each unit. High power appliances or machinery can significantly increase the electrical load. Secondly, the operating hours of the retail spaces can impact the overall load. Businesses with extended hours or specific peak usage times may require additional capacity. Thirdly, future load increases must be considered. Anticipating potential expansions or new equipment installations can help prevent overloading the system. In conclusion, based on the calculations, the minimum service size from the utility company for a building with 3 retail and 3 residential units is 855 volt amps. A meter pack center with a 125 amp circuit breaker should be selected as the service entrance equipment. However, if any unit requires more than 200 amps, further analysis and potential upgrades may be necessary to accommodate the increased load demand. Always adhere to local electrical codes and regulations, and consult with a qualified electrician to ensure the safety and compliance of the electrical system. This ensures that the service is adequate for the building's needs. Consider a situation in retail space A. After initially estimating 175 volt amps, the tenant installs additional equipment requiring a larger electrical load. We calculate the load for that specific unit and determine if it exceeds the allocated capacity. If it does, an upgrade may be necessary, potentially involving a dedicated circuit or an increase in the overall service capacity. Similarly, in residential space RA, a tenant might install high-power appliances or equipment beyond the initial estimate. This requires a similar recalculation and potential upgrade to ensure the safety and functionality of the electrical system. The 125 amp circuit breaker selection is a starting point. However, ongoing monitoring and adjustments may be needed to accommodate changing load demands within the building. This proactive approach can prevent overloads, ensure safety, and maintain the efficient operation of the electrical system. Furthermore, it is vital to understand the diversity factor in electrical load calculations. The diversity factor accounts for the fact that not all electrical loads will be operating at their maximum simultaneously. For example, in a residential unit, the air conditioner, lights, and appliances are unlikely to be running at full capacity at the same time. The NEC allows for applying a diversity factor to reduce the overall calculated load, leading to a more accurate and efficient service size. Refer to the NEC tables and guidelines for appropriate diversity factors based on the type of occupancy and the number of units. Applying a diversity factor can potentially reduce the calculated service size, leading to cost savings. But it's important to apply it cautiously and accurately, ensuring that the system can still handle the expected maximum load. Beyond the diversity factor, consider the concept of demand factor. Demand factor is the ratio of the maximum demand of a system, or part of a system, to the total connected load of the system, or part of the system under consideration. It is typically less than 1, indicating that the maximum demand is less than the total connected load. Applying the demand factor involves estimating the maximum likely load based on historical data, occupancy patterns, and the types of equipment used. This approach can further optimize the service size and reduce costs while maintaining safety and reliability. Bear in mind that using demand factors requires careful analysis and a thorough understanding of the building's load characteristics. It's crucial to consult with experienced electrical engineers to ensure the accuracy and appropriateness of the demand factors applied. It's also important to note that local codes and regulations may specify requirements for demand factors, so compliance is essential. When calculating the service size, consider the voltage drop. Voltage drop refers to the decrease in voltage along a conductor as electricity flows through it. Excessive voltage drop can cause equipment malfunction, reduced efficiency, and potential safety hazards. The NEC specifies maximum allowable voltage drops for branch circuits and feeders. To mitigate voltage drop, select conductors with appropriate size and material, minimizing the distance between the service entrance and the loads, and ensuring proper connections. Voltage drop calculations should be performed to verify that the system meets the NEC requirements and operates efficiently. These calculations should consider the conductor length, current, and material properties. Proper attention to voltage drop ensures a safe and reliable electrical system. Regarding conductor selection, consider the ampacity of conductors, which is the current carrying capacity of a conductor in amps. The NEC provides ampacity tables that specify the allowable ampacity of conductors based on their size, insulation type, and installation conditions. It is crucial to select conductors with an ampacity sufficient to carry the calculated load plus any applicable derating factors. Derating factors account for conditions such as high ambient temperatures, multiple conductors in a raceway, and conductor bundling, which can reduce the conductor's ampacity. Proper conductor selection ensures that the conductors can safely handle the current without overheating or causing a fire hazard. Conductor selection should be based on the NEC ampacity tables and applicable derating factors. Consider the grounding and bonding of the electrical system. Grounding provides a low impedance path for fault currents, helping to prevent electric shock hazards and equipment damage. Bonding ensures that all metal parts of the electrical system are electrically connected, minimizing the potential for voltage differences and creating a safer environment. The NEC specifies requirements for grounding and bonding, including the size and type of grounding conductors, grounding electrodes, and bonding jumpers. Proper grounding and bonding are essential for electrical safety and should be implemented according to NEC guidelines. Grounding and bonding should be inspected and tested regularly to ensure their effectiveness. About overcurrent protection, it protects electrical circuits and equipment from overloads and short circuits. Overcurrent protection devices include circuit breakers and fuses, which are designed to interrupt the flow of current when it exceeds a safe level. The NEC specifies requirements for overcurrent protection, including the sizing of overcurrent devices, their location, and their interrupting rating. Overcurrent protection should be sized to protect the conductors and equipment it serves, while also allowing for normal operating conditions. Proper overcurrent protection is essential for preventing electrical fires and equipment damage. Overcurrent protection devices should be tested regularly to ensure they are functioning properly. 1. Surge protection. Surge protection devices protect sensitive electronic equipment from voltage surges caused by lightning, utility switching, and other sources. Surge protection devices divert excess voltage to ground, preventing it from reaching the protected equipment. The NEC recommends the use of surge protection devices in certain applications, such as dwelling units and critical equipment. Surge protection devices should be selected based on their voltage rating, surge current capacity, and response time. Proper surge protection can significantly extend the lifespan of electronic equipment and prevent costly damage. Surge protection devices should be installed according to the manufacturer's instructions and tested regularly. Let us consider harmonics, which are distortions in the voltage and current waveforms caused by nonlinear loads, such as electronic equipment and variable frequency drives. Harmonics can cause overheating of equipment, voltage distortion, and interference with communication systems. The NEC does not directly address harmonics, but it recommends mitigating harmonics through the use of harmonic filters and other techniques. Harmonic analysis should be performed to assess the presence and severity of harmonics in the electrical system. Mitigation measures should be implemented to reduce harmonics to acceptable levels. Controlling harmonics improves the efficiency and reliability of the electrical system. Regular monitoring of harmonic levels can help identify and address potential problems. Energy efficiency should be considered, as energy-efficient design and practices can reduce energy consumption and lower operating costs. Energy-efficient lighting, appliances, and HVAC systems should be selected. The NEC contains provisions for energy efficiency, such as requirements for lighting controls and motor efficiency. Energy audits can be performed to identify areas where energy consumption can be reduced. Energy-efficient design not only saves money but also reduces the environmental impact of the building. Implementing energy-efficient practices can also qualify for rebates and incentives. Let's discuss emergency power systems, which provide backup power in the event of a power outage. Emergency power systems typically consist of generators or battery systems. The NEC specifies requirements for emergency power systems, including their capacity, location, and testing. Emergency power systems should be designed to provide sufficient power to critical loads, such as lighting, fire pumps, and communication systems. Regular testing and maintenance of emergency power systems are essential to ensure their reliability. Emergency power systems can save lives and prevent significant property damage during power outages. These must comply with all applicable codes and standards. The planning process. Firstly, gather information about the building's electrical needs, including the size and type of the retail and residential spaces, the equipment to be used, and the anticipated occupancy patterns. Secondly, create a load list that includes all the electrical loads in the building, specifying their voltage, current, and power requirements. Thirdly, calculate the total connected load for each area of the building, including the retail spaces, residential units, and common areas. Fourthly, apply demand factors to the calculated loads, taking into account the diversity of use and the likelihood that not all loads will be operating simultaneously. Fifthly, determine the minimum service size required to supply the building's electrical needs based on the calculated loads and demand factors. Sixthly, select service entrance equipment, including the meter pack center and circuit breakers, with appropriate ratings to handle the calculated service size. Seventhly, choose conductors with adequate ampacity to carry the calculated loads, taking into account any applicable damping factors. Eighthly, design the grounding and bonding system to ensure electrical safety and prevent shock hazards. Ninthly, implement overcurrent protection to protect circuits and equipment from overloads and short circuits. Tenthly, consider surge protection to protect sensitive electronic equipment from voltage surges. 11thly, assess the potential for harmonics and implement mitigation measures if necessary. 12thly, incorporate energy-efficient design and practices to reduce energy consumption and lower operating costs. 13thly, evaluate the need for emergency power systems to provide backup power in the event of a power outage. Lastly, document all calculations, design decisions, and equipment specifications for future reference and maintenance. It is necessary to follow all applicable electrical codes and regulations, including the NEC and local building codes. Consult with a qualified electrician or electrical engineer to ensure that the electrical system is designed and installed safely and correctly. Obtain all necessary permits and inspections before commencing any electrical work. Maintain accurate records of the electrical system, including wiring diagrams, load calculations, and equipment specifications. Regularly inspect and maintain the electrical system to ensure its continued safety and reliability. Address any electrical problems or concerns promptly to prevent potential hazards. The service size of 125 amps is suitable for the typical load of the building. However, as usage of electricity increases, there is a potential need to upgrade to the 200 amps.